Good morning, everybody. We have today a lecture which will start with magnetic field, then cover some other topics in electrostatics, but I will also start to make some preliminary considerations that would finally go to electrodynamics and electromagnetic waves. But let's start slowly. So first, let's get back our whiteboard. Okay, we should be there. So if I may, I have been talking last week about, let's say, electric force which affects electric currents, and at the same time we have been studying a process within which electromotive force, voltage, is induced into a moving body which is conductive, and it is induced based on the fact it moves against magnetic field. Now this is a not very intuitive point, and I would like to put here a few remarks. What does that mean, that a body moves through an electromagnetic field? So first, let us have an example which is very unintuitive. So just imagine we have a long stick. A long stick is a magnet which is quite long, so that if you have a stick magnet for example, aluminium, nickel, cobaltum, that's one of the alloys that makes permanent magnets. So if you have a long stick, it in fact has a north pole and a south pole at the ends, and just in the middle of the stick you would not recognize in the vicinity that it's a magnet, because the magnetic field flows through the permanent magnet and then through the ends in big loops between those two poles. But as the stick is long, there is in fact no field at the center of the stick. Now, let us make an experiment. I would use something like a stick. Sorry, I have no magnet, so big aluminium nickel cobaltum magnet, but let's think for a while that this is the stick. So we have a long magnet, and let's make a loop around it. Now you can see that within that loop, a conductive loop. So just consider, after all, a human body is conductive, so that is a loop. So now, what would happen if I just move that stick permanent magnet out of the loop without interrupting the loop? So you have my palms form a contact which still holds. If that was a magnet, aluminium, nickel, cobaltum, that would be conductive. So it still holds, it slides on the magnet, so I have still permanently a loop which has never been interrupted for a single moment. And I had there a magnet, and I retracted out the magnet, so there was the field running through the magnet, and now there is no field in the loop. So the question is, would there be a voltage at any time? And if there would be a voltage induced in that loop, when it will be induced? I mean, we had an arrangement like a magnet Now this is the magnet. I denote magnetic field orientation, so this is the stick, and we have the loop. Let's say there is a pair of contacts that are made, for example, from hard copper, so that they would tend to be closed at any time, but you could get something out of them. And of course, to ask the question whether there is a voltage, we would add a voltmeter. So we've got a voltmeter, a magnet, and we at the beginning have the magnet inside, and then we pull it out.
Sorry?
Yes?
I can't see anything written on the cardboard.
Well, then we have a problem.
Yeah. It's really hard to see.
Yeah.
Yeah, me neither.
Well, okay, I will try, yeah, you know, that's a problem at the moment, but I will try to make the lines thicker.
Thank you.
Did it get better?
Yes, thank you.
Well, so I will have to draw my lines twice. I'm sorry, you know, I am in quarantine, I can't go out, and after all the shops are closed. So I have to do with what I have at my hand now. Sorry for that. So, okay. So now we have the stick, we pull it out of the setup, and would there be any voltage induced? Now remember, we somehow tend to work with the integral form of the equation we had last time. That is, we had a field, now we have no field, so there must be a change and there should be a voltage. We had the other equation which says that the force exerted by electromagnetic field on a charge is first given by the charge value, and then in brackets you have the electric field strength and plus a vector product of the velocity times magnetic field, and that is now a question, because from the first the time derivative of magnetic flux, you would say, okay, there should be some voltage, but then I would ask, and when? And where? I can't carry out the experiment here, but we have carried out many times. Yes, there is no induced voltage, and it should be understood why. Because the voltage should be induced to somewhere, to some part, and that part should be a conductor moving against the magnetic field. Now, having a long stick, you have no field around the center, so the loop has no field inside except for the field running through the magnet. But as to the magnet, you have that field moving together with the conductor. I mean, that magnet is a conductor, and when it moves along with its magnetic field. So it does not induce any voltage into itself. But if you were standing on the magnet, you would not see any movement. And that's important. So in this case, there will not be any induced voltage. If you are looking for a voltage that is induced, you should look for a conductor that moves against magnetic field. Now this is an important point because it's not intuitive. I mean, it's somehow against our everyday experience. And so this is not a case that would produce induced voltage. I will show you another case which would produce induced voltage, and it's hard to believe. Just imagine again that this is a short stick and that is a magnet, and I would have a loop which would be conductive. The magnet itself is aluminium, nickel, copper. Aluminium, nickel, cobaltum. So it is conductive, and if we put the loop this way on the magnet, it would be closed because the magnet is conductive itself and the loop is again conductive. Now if you start rolling the magnet, revolving around its axis, there would be a voltage induced into the loop. But on the first side you can't see any movement. I mean, there is still the same value of electric flux density inside the loop, nothing moved. But the important point is that the magnetic field created by the magnet moves along with him. And at this situation, in fact, the movement is relative. So if you have a standing loop and a moving magnet, it's the same situation for induction, like if you had a standing magnet and a rotating revolving loop. So now the conductor is moving against the field, although you first have to think, because the first thought would be that, well, okay, the magnet is revolving, but it stays on its place, so there would not be any change, but there would be. So the important point again is you have to look or investigate whether there is any conductor that is moving against the magnetic field. And that is the way you will find out whether there is an induced voltage or whether there is no induced voltage. Now this is not easy to get at first sight, and if you can please think it over, how to find out whether a magnet is producing a field that moves against the conductor. You can't see the field, so that's the problem. But you have to think about the source, whether the source moves or whether the source changes the amount of field it generates. I mean, if you have a magnet that could be switched on and off, that again would change the field, and any loop around that is penetrated by the field would get some induced voltage. So this is something that I wanted to tell you as a remark at the end of the story with induced voltage and or force that is exaggerated by the field on a conductor with current. Questions, please. If there were no questions, I will now have, let's say, I will do something which would be like a forward definition in some programming languages. I will talk about something that I will then skip and return to that a bit later. And I will do it because it is something that somehow should change your mind. It is something which is quite against our everyday experience, but it is quite very much needed to understand electromagnetic waves or radio frequency circuits or things like that. But that is something with which we have no direct experience. So I will try to make a tricky, crazy example. You have possibly an experience with a torch, I mean something which has a battery, a switch, and a bulb, so that you can get some light at the dark nights when, for example, camping. Typical torches are created at Ontario, close to Los Angeles. They are called Maglite. They are very robust, and I mean any agent or any criminal in Hollywood films uses that kind of torch. It's very heavy, massive, metallic. It withstands close to anything. And before there have been light emitting diodes, it even had a spare bulb inside so that you could change it if something happened when camping or robbing a bank. So now let's imagine we would have a similar torch, something which has a source, a battery, a very good source, a transmission line, and at the end of the transmission line there would be a bulb. Now we would create really a big torch to see the effects. So let's say that we have a torch with the bulb which is somewhere upstairs, 300,000 kilometers from now, from us. So 300,000 kilometers, it's starting at the ground with the battery, then we have a pair of conductors, and they are going up, and somewhere at the libration center between the Earth and the Moon, there is a bulb which must be a little bit strong to be able to see the light, at least with a telescope. It would have something like 1 kilowatt at least of the power, and that bulb is somewhere over there waiting for the electric current to get it warm and to emit light. So we have that arrangement. I will try to draw it. I will need a little bit more time to make it 2 times. So we have that long transmission line, which has, let's say, the conductor at right and the conductor at left. So this is the transmission line. Here we have a switch and the source of voltage. And on the other hand, we have the bulb, which is a piece of wire placed in vacuum, thanks to Thomas Alva Edison and his inventions. This is something that is working there. So we have a bulb. And at the beginning of the experiment, we will also mention that this is very long, so this is the Earth. And this is very far, not as far as the Moon, but quite far. And let's say that we have a technician over there, a cosmonaut, to be able to place him easily to this arrangement. He should be somewhere 36,000 kilometers upstairs at the geostationary orbit. That's the orbit that if the bulb and the torch was at the equator, there would be a possibility to rotate synchronized with the Earth surface. So like geostationary transmission satellites, there would be an astronaut doing maintenance. So we would probably have a voltmeter and an ampere meter to measure current within the line and voltage, because if he wants to check something, I don't know what else he could check there. So he's sitting somewhere, let's say somewhere here. We have the astronaut with a voltmeter and ampere meter. And he's just measuring the voltage and current. And at the beginning of the experiment, everything is switched off, so that the astronaut would measure no voltage and no current. The bulb at the end would not be lit on, and everything is quite easy, and we are quite happy with the result. We understand what happens at the moment. And also the astronaut understands what happened. No voltage, no current, okay. Now let us think for a moment what a transmission line or a line that guides the power from your battery to your bulb, what kind of apparatus that is from the point of view of the electromagnetic field we have already learned to know. So if we have a transmission line with two conductors, one and the other, once there is electric current that, for example, flows this way there and this way back, then the current that flows through creates a magnetic field. And at the same time, as that, at the other hand, there is a load, and there is a voltage at the load, therefore at the line. In order to have there the voltage on the line, we have to create a proper electric field around those conductors. So the conductor with the current flowing there would be positively charged, and the conductor with the current flowing back would be negatively charged. If we have a source, we would connect the positive part here and the negative part here, and then the line would operate, and those two charges would create electric field in between the conductors, so that the electric field strength, when integrated from here to here, you will give the voltage. So the voltage is possible due to charges that sit on those two conductors. And if we have a transmission line, they do not simply sit there. They are moving. The positive charge is moving towards the load, and then it returns back. So we have there a set of charges that create magnetic field and electric field. Electric field just by sitting on the conductors, and magnetic field by moving, which is called current. Now we a little bit understand the transmission line. Just a short note. For a certain cross-section of the line, it depends on the dimensions, on the shape, but anyway there would be a certain ratio between the voltage and current. We will need some voltage or some charge to create the voltage. And so there is some value which is specific for one transmission line, for one cross-section of the line, depending on the shape and dielectrics and whatsoever, which has a special value which is called characteristic impedance. We will get to that later, but the important point is there is a characteristic impedance which is given as a ratio between a voltage and current. Which voltage and current? Well, if you supply a voltage to that line, you need to charge the line, and that current would be the current bringing in the charge. So if you just connect the source, the line would charge, and to do that it will need for a short time some small current. The ratio between the voltage and this current is called characteristic impedance of the line. Just for a line, for example, consisting of two conductors of this thickness in this distance, I would guess the impedance somewhere to 200 ohms. So a 200 ohm transmission line would be created by two copper rods or sticks that would be this way shaped. So if we have the torch with the astronaut, we would have again, let's say, two transmission line conductors which would protrude from the Earth's surface somewhere 2/3 the way to the moon. And now we have the astronaut there at 36 kilometers height, and he is measuring voltage and current. And so far he is happy because there is no voltage and no current, and that's fine. Now, to begin to make the thing interesting, we would have to switch the power on, the switch which is downstairs. So, okay, we have switched the switch on, and that means that the source has imposed a voltage on the line, just here. But remember, there is a finite velocity with which any information or mass could propagate. And therefore, when we switch this on, it is not known at the end of the line. And by the way, it is not known by the technician, by the astronaut, who is measuring voltage and current at 36,000 kilometers from there. So at that moment, he knows nothing. And what we can see here is that we have a voltage on the line and that we pump some current into the line. In fact, that current causes the line to charge. So that current imposes some charges on the line, and that those charges are moving. The charge part of the line is moving with the velocity of light along it. So at certain time we have some voltage here, but the voltage has not arrived to the astronaut, and we have the current pumped into the line to charge it. And as I told, that current would not be very high because the impedance of that line, the characteristic impedance, would be some 200 ohm. Now that thing arrives to the astronaut, and what would he measure? He would measure the voltage and the current. Let's call that current I0. So he measures a voltage and current, and that's fine. I mean, that's nothing against anything we have so far learned, and we understand that, and he understands that. But that's not the interesting part now. The wave, the information that we have switched on the switch, is now moving ahead. And is moving ahead, and in 1 second from the beginning, it reaches the end of the line. Now, what is at the end of the line? There is a bulb, which has some 1 kilowatt of power, a strong valve that has quite a thick conductor inside that should be made hot. But at this moment, it is placed in vacuum, and the cosmic conditions are not very easy. It's something like -300 Kelvin. So the the wire would not be superconductive at those conditions, but would have a low resistance. Now, there would be a strange situation. There will arrive a wave with some current, and as to the impedance of the line, the ratio of the current and the voltage would be quite different than the one that would be imposed by the load. Just we said 1 kilowatt valve, so if we have 10 volts, it should have 100 amperes. So it's 0.1 ohm at the end when it lights on, but when it's cold, it could be 0.01 ohm at that moment. So it's more or less a perfect short. And a small current which charges the line would not make the bulb to lit on. So we have a problem. We could watch that from another point of view and from the information. Because we have a source, and that source is capable of providing enough current. We have an ideal source with unlimited power delivery on demand. But the source so far could not learn what kind of load is at the end of the line. This is something for our everyday experience very difficult, because our torches are made to fit our pockets, so that the time between we switch on the switch and the light goes on is very short. We can't distinguish it. So I made a big torch to make this mental experiment. And now, what happens at the end of the line? Well, at first there should be the wave going from the source with voltage and the current I0, which is small. And simultaneously, the condition on the valve, which is close to be a perfect short, should be met. And this could be done only if there is a reflection. So that by the moment when the wave reached the valve, the whole line is at voltage V, and there is flowing a current I0 that is charging the line. So it's bringing the charge to the very end where the change is propagating to charge the line to get there the voltage. But now it reached the valve, and at this point we find out that for this very small current there is a zero voltage given the condition of the valve. So what would happen is that, and I will tell it two ways, the wave reflects. It reflects from a short, so it reflects anti-phase. That is, a wave of minus V voltage would be reflected. Or we can say, okay, the information, like with a radar, we have sent a wave, it touched the target, it returns back. So after this reflected wave gets to the source, he would have the first rough idea about the load at the end of the line. And talking in waves of current and voltage, we would have now another wave which has an opposite voltage, so that it cancels the voltage over the line as it passes back. But if we have a positively charged conductor and we want to set the voltage to zero, we have to exhaust the charge out of it, because for zero voltage there should be sitting zero charge on the conductor. which means that the reflected wave has the same direction of current and an opposite voltage. It reflects antiphase voltage, in-phase current, which means that at the place where both waves are present, there would be a strange situation. We have one wave with voltage plus V and one wave with voltage minus V, which is zero voltage. And we have one wave with voltage, with current I0, and one opposite wave with the same current I0, which makes two I0s at the points where both waves have already reached. Now that reaches the astronaut who measures voltage and current and makes him a little bit nervous because his voltage dropped to zero, but the current has doubled. Now he has current and no voltage. Let us him be nervous at the geostationary orbit, and let's watch the wave propagating back. It reaches the source. A source, a perfect source, is similar to a perfect short for any change. So if there is a wave that reaches it, it reflects it like a short that is in-phase current, antiphase voltage. And we have now three waves, the original, the reflected, and the double reflected one on the line. And at those points where this wave propagating upstairs again reaches, we have again voltage. But to achieve that voltage, we have to provide extra current. We have to provide extra I0. But already we have two I0s floating up in this conductor, and we have to provide a new I0 to get the voltage back. So now, when passing around the astronaut, he would notice that fortunately the voltage has appeared again, and he again has a voltage of V. But surprisingly, the current is now 3 I0s. So the current has tripled. Well, and the wave again goes upstairs and reaches the bulb, and it's still cold, so it reflects light from a shore and goes down. And now we have on the whole line, we have again zero voltage and 4 times the initial current. And the fourth wave on the line would reach the source, reflect. We will have again voltage V on the line, but 5 times the current. And after several exchanges, the bulb begins to heat up, and its resistivity and resistance would increase. And therefore, the reflection of the wave would not be perfect, and the waves bouncing there and back would diminish after some minutes. And at the end of the process, we would have the current on that line given by the resistance of the bulb. Now, this in this case would take minutes. Fortunately, in everyday life, we have much shorter transmission lines between our switches and bulbs. And therefore, the whole process gets much faster. Now, this is fortunately because we do not have such a mess. We do not try to make the astronaut crazy. If a technician measures the voltage on the line, he has a single value of voltage and current. But it also has evolved in a way that our minds are not able to catch this idea, because the reality is in understanding that there are waves that start on the source, reflect from the load, and after some time get some equilibrium on that line and the circuit. Now, getting those ordinary sized circuits into operation, we can forget about that, and that is why in circuit theory we learn about currents and voltages, and as far as I know, the basic course of electric circuits does not teach you about any waves. It's not needed. But it's important to understand that this is the physical reality, and we may neglect it and forget about waves as far as the times needed to travel the transmission line are short enough. Well, what is short enough? Is that microsecond? Is that picosecond? Is that femtosecond? Well, and this is an important question. It depends. On what? Well, if you have a DC circuit, and it's not a very strange one, so you can forget it quite easily. If you have a low frequency circuit, well, you might have the chance to forget it as far as the length of the line, the dimension of the system, or the dimension of the element is small enough when compared to wavelength. There is a rule of thumb which says once anything is less than 1/12 of a wavelength, you can forget about waves when thinking about this object. Now, okay, that means that for 1 hertz you have the wavelength of 300,000 kilometers, so that anything again under 25,000 kilometers is of negligible length, and you can forget about waves. Well, okay, what at 50 hertz? Well, we have 3,000 kilometers wavelength, and that means that we have that problem at a very long transmission line, which goes, for example, from Europe to the end of Kamchatka, or from Europe. There is no direct line through Mediterranean Sea, but well, okay, if you have a cable from Europe to America, if you have a cable from Europe to Africa, it could be that you have to consider this something which is strange for DC circuits. And now your mobile phone uses frequencies up to 2 gigahertz, 2.4. In fact, if you have Wi-Fi in the upper band, you can get even 5 gigahertz in your mobile phone. And now 5 gigahertz means that you have a wavelength of some 6 centimeters in the presence of no dielectrics, and therefore anything which is longer than 5 millimeters has to be described using waves, not ordinary fixed values of current and voltage. So those applications like mobile phones, telecommunications and others, microwave ovens, are those that cause that we have to consider also wave effects. But the important point is that at the beginning we have time delay that is incurred by the signal when propagating through that transmission line or media. And this something gets important once the dimension of that line gets big enough to be comparable with the wavelength. And the rule of thumb is 1/12 of the wavelength. Now, this is something new, it's a new point of view that is, it's strange, and our minds oppose to anything that is new and try to tell us that this is not true. The old things I have learned so far are true. So I did this crazy example for you, like a small seed. We will not use it in our remaining lecture today, but I will leave it in your brains for some time before we'll start with waves, because I hope that it will have some effect and it will help you to understand the topic then. The important thing is the field is, the world is full of waves, of electromagnetic waves, and understanding waves means that we have to understand time delay that we do not experience in our everyday life. Ladies and gentlemen, your questions. Hello again. Are there any questions? Well, okay, I do understand fully, or you are shocked, but anyway, both situations are a result of the example. So now we can get back to electrostatics, our old, nice electrostatics with no traveling waves. And the thing I would like to raise now is the question how to find out a dragging force of an electromagnet. Just possibly you have traveled by a tram in Prague, and such a tram has got three kinds of decreasing its speed. The first is that they just let the motors work to a load, which decreases the speed and could be even used for recuperation. So if there is a proper arrangement in the network, a tram going downhill could generate power which is consumed by another tram which is going uphill. Very nice. But this is of a limited power. So if you need to decrease your speed faster, you can't use that economic way. And there is a second type of apparatus, which is two metallic jaws that get the grip, and they grip not directly to the wheels but close to the wheels to a special installment, and again decrease the velocity of the tram, this time definitely changing the heat into the kinetic energy into the heat. This could provide much faster decrease of the velocity. But the sad truth is that there still might be a need for an even faster slowdown. And there is a third system in the tram, which by the tram drivers are called booths. There are special just boxes you can see between the wheels, a kind of something that looks like a big metallic box, but in fact inside that is a strong electromagnet. This electromagnet is fed not from the outer network but from the accumulator of that tram, so it would work even if there is a blackout. And this electromagnet is used for emergency stop-downs. And if that emergency gets up, then the current is switched into this magnet. It sticks heavily to the rail, which is metallic, so there is a closed magnetic loop. It has the attractive force of 5 tons, and the tram has 4 of those at least. And this system is able to stop the tram very dramatically on the expanse that people would possibly somehow fall inside, that the slowdown would be very fast, but sometimes might be needed. For example, the metro cars do not have such an apparatus because it's not expected that something suddenly happens. So for a metro, it could take, from the full velocity, it could take some 300 meters to stop. If it runs downhill, it could be even more. But for a tram, it could stop much faster than a car because it has a special apparatus, which is an electromagnet that really connects it with the rail. And in some cases, it even happened that the rails have been pulled out of ground with this fast slowdown. But if we were the electrical engineers who would have to design this pretty piece of a tram, we would have to somehow have the ability to calculate the force, the attractive force of the magnet. And now we do not have anything like with electric field, where we had electric field intensity times the charge makes the force. We would have to find out another way how to calculate the force. And in fact, this way is called the virtual work principle. The virtual work principle, what does that mean? Well, we have to consider where the force comes from. And the reply is quite simple. To have a force, you need to have some change in energy. So, if you have a small movement of an object, for example, if I would try to find out the dragging force of this pencil, and if it was magnetic, I could use a virtual work approach in that manner that I would calculate the energy of that arrangement with the pencil at one point, and then I will slightly move the pencil and examine whether there is an increase or decrease in the energy of the field. Now if I move it in reality, the field would change very much, and that's not good for calculating the instant force at one position. But what if I only make a differential movement, which is called a virtual movement, because in fact I do not move it, I only think that if I moved it a very tiny little bit, it would somehow change the energy. And now we have the Newton's law, which says that the force would result in a change of velocity. So what we have force on the left side, mass on the right side, and acceleration. So force is a product of mass and acceleration. At the same time, to carry out work, let's denote it A, the work is carried by a force over some path, and that could be written as A is force dot product with the path L. Now we could make it vectors. The result of a dot product is not a vector, we have two vectors, force and the path. So if we know that there is some movement of a body caused by a force, we will have a mechanical work of A if the body moves some path caused by the force F. But there is nothing for free in the universe. If you get some work, it must be on expense of something. We have the energy conservation principle. And this something is the energy of the field, in our case of magnetic field, so that we would have some field which must have decreased its energy if we have gained positive work. So if we, for example, have got an acceleration of something due to magnetic field, it must have been on the expense of the energy of that field. And we already know that the energy in the magnetic field has some density. We have denoted the density as small w, and we know that small w, that the density of magnetic field, small w magnetic, is 1/2 of the product of magnetic flux density B and magnetic field intensity H. Just a question, is it at least a little bit readable?
Yes.
Thank you. So now we know the density of the energy, and therefore we might be able to examine the change in the energy. And we'll do that with an example which is, by the way, taken from the apparatus on the tram. So I will first draw a little bit how that is arranged, and then we will find out the dragging force that makes the several ton tram to stop at a few meters. Admittedly, with the problem that the passengers do not stop and they still move inside the tram, which is the problem, so it could be used only at really emergencies. So we have something which is called by the letter E as the shape of the magnetic circuit. I will draw it again a bit schematically. So it's like a letter E, which points down, but the important point is that this is the same width, this is the same width, and the center part of the E is double the width. So in fact it is this way symmetric. Why the center part is twice the width? Because then you have two halves that are composed of sticks or bricks with the same width and therefore the same magnetic reluctance. But as the magnetic flux flows this way, the magnetic flux in this part is doubled, and in order to keep the saturation far enough, the width is doubled in the central part. So this is the E shape of the magnetic circuit. And you have the rail under that. So now we have the rail and the magnetic circuit of the brake, and now we put a number of turns, a winding, on the central part. So we have an inductor, we have an electromagnet that puts down the magnetic field by switching or connecting this winding to the battery of the tram. Now it's made out of a solid wire and the current is quite high. So there are hundreds of amperes when switched on. And as you remember, our magnetic flux would be proportional to the number of turns and current and permeability of the circuit, and inversely proportional to the length of the flux line. Now if we would decrease the complexity of the problem, we can consider that the magnetic part of the circuit, I mean the steel one, that is the rail, and the magnetic core in the brake are magnetically ideal conductors. As far as we have some interruption filled by air whose permeability is 1000 times smaller, the whole or most of the reluctance of the circuit is contained in the air gap here. And by the way, most of the energy of the magnetic field is contained in this gap. So what is the density of energy? As we have the double flux here and the double surface or cross section, the energy density in all three air gaps would be more or less identical, and it would be, again, W is 1/2 of BH Now we can omit vectors since everything is collinear. And we can continue and put down that this is mu 0 because it's in the air, and mu times h makes b. We could put mu 0 h squared divided by 2. So now this is the energy density within the air gap of that break. And now let us start to think about the virtual work principle. So if we moved the braking part on the tram a little bit closer down, then there would be more or less no change in the current here. The magnetic circuit would not change very much, but it would change here in the air gap. How it would change? Well, in fact, the movement would decrease the gap, and the energy that has been in that part of the gap would change into mechanical work. So if I, for example, magnify this piece, we have a solid magnetic circuit. And we have the steel bottom. And now if we move it a little bit to here, we would make something which is a differential dx movement. This is d, this is x. So we move the brake only differentially down, and now we should find out what the energy in the field that was originally in the gap but disappeared was. Now why we do only a differential movement? Because if we move a lot, then the reluctance of the total circuit would decrease and the magnetic flux in the air gap would increase. But if we make only a differential movement, then we can count on the rest of the circuit being intact. And therefore, if we make only a differential movement down, we could calculate the energy that was drawn out of the field with the original values, B and H or H squared. So now what would be the energy? Well, we have some surface here, double the surface here, and the same surface here. So 4 times the surface of the cross-section of this part of the magnet is the total cross-section that has moved downstairs. So let's call this surface S, big S, as a surface the cross-section of that magnet. And now if we move it down, we move this, twice this here, and again this 4 times the surface, times dx, so we have a volume of 4s times dx. So the total energy is the volume times the density. And I will now write the equation. The total energy caused by, or energy change caused by the movement would be 4 times the surface or the cross section of the right part of the magnet, 4s, times the height or the movement dx, and this now is multiplied, this is the volume that has disappeared from the gap, and we should multiply that by the density of the energy, which would be mu 0 h squared and we should divide it by 2. This is just rewriting the formula for energy density of the magnetic field. Now this is the total change in the energy of the field, and this has been achieved by a movement over a distance of dx. Remember that the mechanical work is equivalent to a product of the force and the path. So this must be equivalent to the force times dx. The path is dx, so the force times dx is an equation for the mechanical work. So in fact we have set up an equation when we have the change of the energy of the field on one side and the mechanical work that has been carried out by the change on the right side. Now you can see that based on this we can cancel the displacement dx on both sides of the equation. So we can cancel the x here and we can cancel the x here, and what we have been left with is an equation for the force. It is equivalent to 2 times this surface mu 0 h squared. And we have been able to calculate the force that affects the brake at the beginning or when there is still air gap, and this is our equation for that. So I have demonstrated that using a principle which is called virtual work principle, we can find out a force that affects objects, and we can do that by finding out the difference in the energy of the total field that is caused, or that would be caused, by a differentially small movement of the object. The virtual energy principle or virtual work principle is very important because you can use it for magnetic circuits, you can use it also in electrostatics. In electrostatics you can easily find out how one charge attracts other charge, but what if, for example, you would like to attract dielectrics into electrostatic field? It really happens, it works, but you can't see any charge there. But with the virtual energy principle you can again find out how a dielectric is sucked into electric field. So this was a virtual energy principle and its demonstration for magnets. Now I would like to get your questions. Are there any questions?
No, I'm fine, thanks.
Okay, was anything irreadable so that I should put it down once more?
I have been able to read everything.
Well then, that's fine. I hope that in the video it would be also good. So, okay, so we have now demonstrated the virtual work principle, and I will switch to another topic after another 5 minutes break. I would continue with a new topic, and I can promise you that there would be something unexpected at the end of this topic. Well, the topic would be the Poynting vector. I will first define it and later find out the behavior of this vector. So the Poynting vector we denote big S, like surface, but big S. And it is a vector, as I told. And it is defined or given by a vector product of the electric field strength E, which is a vector. And the magnetic field intensity H, which is again a vector. Now, if you would carry out that vector product, you would get an interesting result, because the result produces the Poynting vector, but the unit of that is watt per meter squared. And that brings us to the physical meaning of that vector. The Poynting vector tells us the direction in which energy propagates or moves, or we can say in which power moves and propagates, because after some time of propagating power we get some energy, and the magnitude of the vector tells you how much energy flows through certain cross-section, 1 square meter. So this vector is very important in establishing our knowledge of energy propagation, how the energy from the source gets to the load. As any simple equation, this needs careful attention. That equation is meaningful in the case that it refers to one source. So if this electric field and magnetic field as well are created by one source, that could be one battery that feeds the circuit, for example, that could be one antenna that radiates power. But if it is created by one source, in that case it gets a power transmission. Why I'm telling that? I get, say, once a week an email from somebody who thinks he has invented perpetuum mobile because he has brought a plate condenser, a plate capacitor. He puts there some voltage, so he creates electric field vertically. Then he brings a permanent magnet and places it around it. So he creates a magnetic field which is horizontal. And he says, hey, I have found a source, and now he calls it free vacuum energy or public energy or free energy or anything. And he thinks that by simply creating two distinct fields, one magnetic, one electric, that have perpendicular field lines, he created a flux of energy that is for free, because he notices that the capacitor stays charged. He notices that the permanent magnet stays intact. And that's both correct. But there is no energy flux out of this arrangement, because those two fields, electric and magnetic, do not belong to the same source. So the equation needs to be understood well. So now, after we know that, we have to understand the equation. After we know that the Poynting vector is capable of describing power transmission, I would like to show you the surprise I have promised a few minutes earlier. Let us find out the energy transmission, for example, by a wire. So we have a wire that connects the source and the load on the other hand. Let's think it's an ideal conductor. So we would have a wire, and the wire is going from a source which is somewhere there to a load which is somewhere in that direction. As you remember, there must be some second wire bringing the energy back, but let's investigate the situation at one wire only at the moment. So we have the wire which has a current flowing into the board, and now this wire creates, or the current flowing through that wire must create a magnetic field around the wire. we have already investigated this using Ampere's law, and the result was that the field has a form of concentric circles around the conductor. So the field lines look like this. Well, that should have been circles. And as to the strength, as to the intensity, it follows that magnetic field intensity H is directly proportional to the current that flows through the conductor and inversely proportional to 2 pi r, where r is the distance from the center of the conductor. So we have here a radius of r so the field is decreasing with the distance. At the same time, as we have already investigated today in the first part of the lecture, there must be a charge sitting on the surface of that conductor which is responsible for electrostatic field that will result in the voltage we measure at the conductor. Because if we try to transmit power from the source to the load, we need both voltage and current. So there must be voltage. It's due to a charge sitting on that conductor, and as you remember, for a straight conductor charged by tau per meter, there is an equation for the electric field strength around it, and that is E the electric field strength is directly proportional to the charge density tau, which is the charge per 1 meter of the conductor, and it's inversely proportional to 2 pi r, where r is again the distance from the axis of the conductor. Now, at any point, you can find, I will draw, this is the line of the E. It goes perpendicularly to the field lines of the magnetic field. So in this case, we can make the vector product much simpler, because as to the magnitude of the pointing vector, we can simply multiply the magnitudes E and H and get rid of the orientation and direction, so we can convert the dot product into an ordinary product. So let's make it. What would be the value of the pointing vector, this S, which is equivalent to current times charge density and divided by 4 pi squared r squared. Well, okay, so it seems that the energy propagates along that wire. We can find out also the direction. If we have the E in this direction, H in this direction, so at this point we have two perpendicular vectors, this and this, we can find out that the energy goes inside to the board and therefore it propagates along that conductor. And we find out that the energy density falls down with a square of the distance. Now there are a few remarks on that. First, this means that if you walk under a power line, for example from Temelin power station, that's a high voltage line and it carries something like 1 gigawatt of power. That means that most of the power, of course, propagates in the vicinity of the conductors. But anyway, if you are walking around, there are some kilowatts passing through your body anyway. The energy is not confined just to the vicinity of the conductors. But possibly the main surprise, what happens inside the conductor? Well, inside the conductor, you have some magnetic field possibly due to the current density inside the conductor, but you have none or negligible electric field strength. And that means that the pointing vector inside a conductor is negligible. That is, the conclusion is that the power propagates from the source to the load alongside conductors, but not through the conductors. Inside the conductor we have no power transmission to the load. And that may be a surprise. The power propagates around transmission lines, but not inside the conductors. On the other hand, without a conductor, we would not be able to create an electric field pattern that would then result in energy transmission. So we need the conductors to create the electric field and to carry the current, which creates magnetic field. But the power transmission itself runs around the conductor. That is something that is against our everyday experience. We can't sense the power transmitted around those conductors. What we can sense is the power delivered to the load. And our first guess would be that the power is distributed through the conductors. After all, most of people think that. But you as electrical engineers should know that this is not the case. The power is distributed along the conductors. It runs around them with biggest density just at the conductor surface, but it stays out of the conductor. And as I will show you later, we try to keep it out of the conductor for good reasons. Now, your questions, please.
Could you tell what letter do you use in a formula where S is equal to current and then that second letter?
The second is tau, which is the charge per 1 meter of of the conductor. And remember, we use the same letter when we have been describing an electrostatic field around a thin wire that is charged. So it's Coulomb per meter, the amount of charge that is sitting at 1 meter section of that wire.
Thank you very much.
Welcome. So if this is the case, I would like to comment a little bit on this situation in the case it is not as ideal as we have investigated so far. What if we have not an ideal conductor, but we have a good conductor? I mean copper, aluminium. So if we have a real transmission line with lossy conductors, we know that according to Ohm's law, if we have a finite conductance, we have some voltage on it. So for a real conductor, I will now turn the conductor so that we would have a cylinder going this way. So we have a cylinder going this way. This is the conductor surface. Within that conductor, the current is running that way. The conductor is a cylinder placed this way, so we have the electric field strength around the conductor pointing upstairs in our cross section, and there is a magnetic field which runs out of the board at this part, so we denote that by an arrow, a dot in the circle. So we have the electric field and the magnetic field of that conductor. So far we have only considered the case of a lossless conductor. So we have only perpendicular electric field strength and circular magnetic field. But what if this conductor is quite conductive but not infinitely conductive? Then when passed through by a current, there is a tiny dropout in the voltage, which means that there would be a tangential component on the surface of the conductor. Well, I will make the picture for a very bad conductor to enable you to see anything. So then there would be a component on the conductor. So there will be an electric field strength in this direction. And the resulting electric field would then bend and not be perpendicular, but it will bend in the direction of the propagation of that power. If this happened, we have still the magnetic field intact. I mean, the current does not vanish. Nothing is those electrons traveling through that line. But we have the electric field a little bit bent to the direction of transmission. Now, if that happened, it would mean that the Poynting vector that originally was E times H and was exactly along that transmission line would bend with the field. So now the Poynting vector points this way. And on the lower side it points that way. In fact, we can decompose that Poynting vector into two parts. One is propagating along the conductor, as before, and the other propagates directly to the conductor. you have any explanation why there is a part of the pointing vector or a part of the power propagating to the conductor from outside? What is the physical meaning of that? Well, I will help you a little bit. We have a conductor with finite conductivity. That means not only that we have a small tangential component of electric field strength on its surface, it also means that there is a voltage drop. And we have a voltage drop at an element with some current flowing through. So the result of that is electric heat. We have a conductor that becomes hot. For outer transmission lines, we can get up to 10 amperes per millimeter square. That's a good rule, which will make the conductors warm but not melting. But this means that there is some thermal energy. But this thermal energy could not be born of nothing. So there must be some other energy that covers this expense. And to get this energy, we have to get some energy of the electric field of the propagating power back to the conductor to cover these losses. And as inside the conductor we have zero or close to zero electric field strength, we do not have the energy there. So there is no energy to cover the losses. We have to get it from elsewhere, and it should be the energy connected to that propagation. So, in fact, we could think of that like if at the source puts voltage and current to the conductor, which is equivalent to creating a big bubble of energy around the conductor. There is the energy given by this, the energy density or the power density is given by this equation. So it's inversely proportional to the square of the distance. But it's sitting around the conductor and it's propagating along the conductor. But as the conductor is lossy, a part of that energy is propagating into that conductor, and this energy covers heat losses of the energy transmission, which does not result in a decrease of the current. By the way, it flows through the conductor and has not any possibility to leave the conductor, at least on a well-made transmission line. But as there is a small tangential component of the electric field strength, it results in a decrease in the voltage. So along that line, the voltage slightly decreases, and therefore the electric field strength decreases, and the thermal losses within the conductors that guide the current are covered on expense of the electric field or around those conductors. So we lose voltage, and we lose voltage depending on the value of the current flowing through the line. And that's, for example, why you have tolerances on your devices. It is normal, or it is against nothing if your voltage is within plus minus 10% limits. So it, for the nominal value of 230 volts, you can get 23 volts more or less, and it's still okay. And this depends on the consumption in the network. If nobody switches anything on, you would get 250 volts. If the current increases, the losses in the conductors would cause the voltage measured at your socket to decrease, and this is all given by the way I have shown you here. Then with the pointing vector, this is the story. So now, after this explanation, you understand the way power is transmitted using a transmission line from a source to a load, and you not only understand that it is transmitted using a transmission line, but in fact around the transmission line, you also understand where the losses come from and how they are covered from the energy originally supplied by the source. Your questions, please. Still no questions? I will just look the chat. I have not. Okay, no, nothing in the chat. So okay, so we have today completed several important parts. We have been discussing the virtual work principle. We have discussed induction of electromotive force into conductors moving within magnetic field, or better to tell, moving against magnetic field. And we have been discussing pointing vector and the transmission of power that is caused by electromagnetic field. Now, are there any more questions? Well, we have but 5 minutes to the end of the lecture, so we will reserve that time and use it possibly next time, because in 5 minutes we would possibly do no big science today. So I'm going to quit the lecture if there is still no question. Well, okay, then I have the last short topic. I will be again available for consulting on Monday evening. That is 6 of a quarter to 6 in the evening. I will send you again an invitation, which is not compulsory, just if you need some consulting. That's the first point. Second point, I hope to get a better pencil by next lecture, or possibly I will get released out of quarantine and we will be able to come to school, and there is a number of pencils, of course. I wish you good health. Don't hesitate to ask me questions if you have any, and I promise you some new contest for the next lecture. Well, that's all. So still no question? Okay then. Is there a question?
Are we going to talk about waves and
Well, yes, we have some two small topics from electrostatics that I have not covered yet, and then we will start with electromagnetic waves. We will start
Thank you.
slowly. We are drawing into electrodynamics, and we are somehow something around midterm, which is a good time to start with waves, because you have had all those topics we have addressed by now, at least somehow, in your physics at secondary schools. So it seems you hear new things, but they do not seem to be so new to you. But electromagnetic waves are something that for most of you would be new. And that is, we have to leave sufficient time for that in our lectures. But anyway, it's a thing for next week. So if there are no more questions, please keep safe. Thank you for attending my lecture. I'm looking forward to meet you again in 1 week. Bye.